Gravity is one of the most fundamental forces in nature, and yet it's one that many of us take for granted. Every day, we experience its effects without thinking twice. Gravity keeps our feet on the ground, makes objects fall when dropped, and governs the motion of celestial bodies like planets, stars, and even light itself. But gravity is more than just a force that keeps us grounded on Earth. It is a force that governs the entire universe, shaping the orbits of planets, the formation of stars, and even the fate of galaxies. Today, we're going to explore this mysterious force in more detail and understand how it shapes the universe. The concept of gravity was first formally described by Sir Isaac Newton in the 17th century. Newton's law of universal gravitation states that every object in the universe exerts an attractive force on every other object, and the strength of that force depends on two factors: the masses of the objects and the distance between them. Essentially, the larger the mass of an object, the stronger its gravitational pull. And the closer two objects are to each other, the stronger the gravitational force between them. This concept seems simple enough, but it has profound implications. For example, the Earth's gravity pulls objects toward its surface, which is why we stay firmly planted on the ground. But gravity doesn't just affect small objects, it also governs the motion of massive bodies like planets and stars. The Earth orbits the Sun because of the Sun's massive gravitational pull. The gravitational force between the Earth and the Sun is what keeps Earth from flying off into space and ensures its steady orbit. One of the most interesting things about gravity is that it acts over vast distances. The force of gravity is what keeps the planets in our solar system in orbit around the Sun. It's also what governs the movement of moons around planets, like the Moon's orbit around Earth. The strength of gravity decreases with distance, but it never truly disappears. Even objects far away from each other, like the Sun and the distant planets of our solar system, continue to influence each other's motion through the gravitational force. While Newton's laws of gravity helped explain many things, they were later expanded upon by Albert Einstein's theory of general relativity in the 20th century. Einstein's theory revolutionized our understanding of gravity by suggesting that gravity is not a force transmitted through space, but rather a result of the curvature of spacetime itself. According to general relativity, mass and energy cause spacetime to curve, and objects move along this curved path, which is what we experience as gravity. To understand this better, imagine a large trampoline. If you place a heavy ball in the center of the trampoline, the fabric will stretch and curve under the weight of the ball. Now, if you roll a smaller ball across the trampoline, the smaller ball will be drawn toward the heavy ball because of the curvature of the fabric. Similarly, planets, stars, and even light are all affected by the curvature of spacetime caused by massive objects like stars and black holes. Instead of thinking of gravity as an invisible force pulling objects together, we can now think of it as the bending or warping of the very fabric of spacetime, which dictates the motion of everything in the universe. One of the most fascinating consequences of general relativity is the phenomenon known as black holes. A black hole is an object with such a strong gravitational pull that not even light can escape its grasp. Black holes are formed when massive stars collapse under their own gravity at the end of their life cycle. The gravitational pull inside a black hole is so strong that it warps spacetime to the point where there's a singularity, a point of infinite density where the laws of physics break down. Black holes are invisible, but we can detect their presence by observing how they affect nearby objects. For example, if a star passes too close to a black hole, the black hole's gravity will pull on the star, causing it to stretch and distort. This process, known as spaghettification, occurs because the gravitational pull is stronger on the part of the star closest to the black hole, stretching it out into a long, thin shape. As this material is pulled into the black hole, it emits powerful radiation that can be detected by telescopes. In fact, scientists have recently captured the first ever image of a black hole's event horizon, the point of no return beyond which nothing can escape, in the galaxy M87, providing stunning evidence of the existence of these cosmic giants. Gravity also plays a critical role in the motion of celestial bodies across the universe. Our solar system is a prime example of how gravity works on a cosmic scale. The Sun's gravity holds the planets in orbit, preventing them from drifting off into space. But gravity also affects the smaller objects in our solar system, such as asteroids and comets. These objects are not bound to the Sun as the planets are and can be influenced by the gravity of other planets. For instance, Jupiter, being the largest planet in the solar system, has a gravitational pull that can alter the orbits of asteroids, sometimes pulling them into the inner solar system, where they become comets. Beyond our solar system, gravity governs the motion of entire galaxies. The Milky Way, the galaxy we live in, is held together by the gravitational pull of its stars, gas, and dark matter. This gravitational pull keeps the stars and other objects in the galaxy from flying off into space. Similarly, gravity causes galaxies to move toward each other, eventually forming clusters of galaxies. The gravitational attraction between these clusters leads to what is known as cosmic collision, where galaxies can merge to form even larger galaxies. Another interesting effect of gravity is its impact on time. According to Einstein's theory of general relativity, time moves slower in stronger gravitational fields. This phenomenon, known as gravitational time dilation, means that time passes differently depending on how close you are to a massive object. For example, if you were to spend time near a black hole, you would experience time much more slowly than someone far away from it. This effect has been tested and confirmed using atomic clocks on satellites orbiting Earth, which show that time actually moves slightly faster in space than on Earth due to the difference in gravitational pull. Gravity is also responsible for the tides on Earth. The Moon's gravitational pull on the Earth causes the water in the oceans to bulge out, creating high tides. As the Earth rotates, different areas experience high and low tides. The Sun also exerts a gravitational force on the Earth, but its effect on the tides is less pronounced than that of the Moon because it is much farther away. The interaction between the Moon's gravity and the Earth's oceans is a perfect example of how gravity can shape the Earth's environment, influencing everything from ocean currents to the behavior of marine life. As we continue to study gravity, there are still many questions to answer. For example, while general relativity has successfully explained how gravity works on large scales, scientists are still working to reconcile gravity with the principles of quantum mechanics, which governs the behavior of particles at the smallest scales. This quest for a unified theory of gravity and quantum mechanics is one of the most exciting challenges in modern physics. In the end, gravity is a force that shapes everything we know, from the motion of the stars to the tides of our oceans. It's a force that governs the universe, providing the framework for the existence of galaxies, solar systems, and life itself. Whether it's through the curvature of spacetime, the formation of black holes, or the motion of celestial bodies, gravity is an ever-present force that continues to awe and inspire scientists as they seek to unlock the mysteries of the cosmos.